This is SpaceTime, Series 29, Episode 62, full broadcast on the 25th of May, 2026. Coming up on SpaceTime, the most primitive galaxy in the known universe, understanding the true nature of the Muon, and a spectacular meteoroid streaks across the skies of Sydney. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have identified the most chemically primitive galaxy in the known universe, a stellar city dating back more than 13 billion years. The findings, reported in the journal Nature, suggest that this ultra-faint galaxy, catalogued as LAP1b, has a record-breaking low oxygen abundance of just 1/240th that of our Sun. This chemically primitive state, coupled with an elevated carbon-to-oxygen ratio and a dominant dark matter halo, suggests that this ancient galaxy is one of the long sought-after ancestors to the mysterious fossil galaxies found near our own Milky Way galaxy today, thereby providing an historic window into the earliest and most primitive stages of galaxy evolution. The discovery is based on new spectroscopic observations achieved by NASA's Webb Space Telescope. And aiding in the find was gravitational lensing. This involves light from a background galaxy being bent and magnified by the mass and hence gravity of a closer foreground galaxy. This allows astronomers to peer further back in time, giving them a rare glimpse of the early universe. Just after the Big Bang 13.8 billion years ago, the universe was fairly simple, consisting only of light elements such as hydrogen and helium. The heavier elements necessary for life, such as oxygen and carbon, didn't yet exist. They were first forged in the nuclear furnaces of the very first stars. For decades now, astronomers have been trying to find the moment these first-generation stars, known as Population 3 stars, began scattering the seeds for life across the cosmos. However, the earliest galaxies hosting such young primordial stars have remained so small and faint that seeing their chemical makeup was considered nearly impossible, at least until now. The study's lead author, Kimiko Nakajima from Kanazawa University, says finding a galaxy in such a primitive state was an astonishing achievement. It's a chemical signature that clearly indicates a primordial galaxy caught shortly after its formation. Beyond its primitive nature, this galaxy exhibited a high carbon-to-oxygen abundance ratio. And this unique chemical fingerprint aligns closely with the theoretical predictions for the material dispersed by the supernova explosions of the universe's first stars at the end of their lives. Nakajima says, usually we act like cosmic archaeologists, trying to guess the past by looking at old stars in our own neighbourhood. But now we can analyse gas directly from the original scene, some 13 billion years ago, witnessing the very moment when a galaxy first inherited the chemical building blocks that created the universe's first stars. Nakajima and colleagues also discovered that LAP1b is incredibly light in terms of mass, less than 3,300 times that of the Sun. That implies that most of the mass in the galaxy does consist of invisible dark matter, that mysterious stuff that makes up 80% of the universe, but which scientists have yet to isolate. Now, this feature, together with its unique chemical makeup, makes LAP1b a near-perfect match for the ultra-faint dwarf galaxies which are found near our own Milky Way galaxy today. They're composed of ancient stars over 12 billion years old, and are often described by astronomers as fossils of the universe. And astronomers suspect that these may well be the remains of the universe's earliest galaxies, because they too lack heavy elements. But astronomers have never had a direct link, at least until now. This is SpaceTime. Still to come, understanding the true nature of the Muon, and a spectacular meteor streaks through the skies of Sydney. All that and more still to come on SpaceTime. Physicists have achieved a major breakthrough in understanding the discrepancy between experimental measurements and theoretical predictions of the magnetic properties of the muon, a heavier cousin of the subatomic elemental particle called the electron. The findings, reported in the journal Nature, are addressing a problem that's been debated by scientists for decades. This new research provides the most precise calculations to date of a key component underpinning the muon's magnetic moment. The muon is a subatomic particle similar to the electron but around 200 times heavier. Muons are produced when high-energy particles from space, called cosmic rays, hit the Earth's upper atmosphere. Roughly 50 of these muons pass through the human body every second. Like the electron, muons behave as tiny magnets. The strength of this magnetism, known as its magnetic moment, has long served as a powerful test for the standard model of particle physics, the very foundation stone of science's understanding of the universe. But for years, the strength of the muon's magnetism has exhibited a persistent discrepancy between theory and experiment, and that hints at the possibility of undiscovered physics beyond the standard model. Peeking into the window of undiscovered physics is important because it may provide answers to some of the big mysteries of science, such as exactly what dark matter is made of. The study's lead author, Finn Stokes from Adelaide University, says the new work finally resolves this discrepancy, reinforcing the standard model rather than breaking it. He says the research focuses on the most uncertain part of the theoretical prediction, the hadronic vacuum polarization contribution, which arises from the complex interactions of quarks and gluons which are governed by quantum chromodynamics. Quantum chromodynamics is the fundamental theory describing the strong nuclear force that binds quarks and gluons together to form protons, neutrons, and other subatomic particles. It's a core component of the standard model of particle physics. Stokes says these strong nuclear force effects are really difficult to calculate with high precision. So to overcome this challenge, Stokes and colleagues used a novel hybrid approach that combined large-scale computer simulations with experimental laboratory data. Using some of the world's most powerful supercomputers and a technique known as lattice quantum chromodynamics, the authors performed calculations at a higher resolution than ever before, thereby allowing them to significantly reduce uncertainties. And the new result is almost twice as precise as the previous consensus. They determined the hadronic vacuum polarization contribution with unprecedented accuracy, leading to a new standard model prediction for the muon's magnetic moment. And this updated prediction agrees with the latest experimental measurements to within just 0.5 standard divisions. Stokes says the work demonstrates the power of combining theoretical and experimental techniques to tackle some of the most challenging problems in physics. He says it's a major step forward in science's ability to test the standard model, and with this reduction in uncertainties, physicists can now compare theory and experiment with unprecedented precision, providing a remarkable validation for the standard model to some 11 decimal places.
There's been, a long ongoing sign of new physics in the magnetic moment of the muon for over 20 years, and so there's been a long ongoing theoretical program to try and meet the experimental program, and there's been this discrepancy that's been gradually growing in significance over the years as we get the results more and more precise. And recently, my theory group, as this result got to sort of the level that we would usually announce an actual discovery of physics, my group came out with a new theoretical calculation that identified what seems to be a problem in the old theoretical calculation and updated the value, and agrees really well with the experiment now, which means these signs that we thought that there seemed to be new physics because our theory and our experiment weren't lining up are maybe disappearing.
You achieve this data not by looking at the big picture, but by breaking it down into a series of smaller exercises.
Yeah, so there was a whole heap of different groups around the world working on small pieces of the problem, and we worked on a very specific one called the hadronic vacuum polarization, which is looking at the strong nuclear force, and then basically different groups looked at different forces and then different specific contributions from those forces. So the strong nuclear force is what holds, even smaller than the protons and neutrons, the quarks that make them up, holds those together to form the protons and neutrons. And then there's a little, it's called the residual strong force, the little leftover bit after it's bound those together that then binds, as you say, the protons and neutrons together to make the nucleus.
Beyond the standard model, finding something there is important because the standard model doesn't explain dark matter or dark energy.
Yes. So we kind of know that there has to be something beyond the standard model because our observations of the universe and how galaxies and even larger scale objects behave clearly indicate the gravitation, the gravitational attraction within these objects is different to what we expect. So we know there must be dark energy and dark matter. And so we are searching for something that could be dark energy and or dark matter. And this has to exist beyond the standard model because nothing in the standard model can do that. And so, yeah, hopefully we can find something beyond the standard model that'll give us insight into what these phenomena are.
What are you hoping to find? An axion?
I think the axion is something that is really interesting, and there are some promising signs for that. It's definitely something my group has been interested in looking into, particularly the QCD axion. I think for what we're currently seeing, the sort of residual tensions we see in the Muon magnetic moment, the strongest candidate is some kind of dark photon, or what's sometimes called a Z prime boson. So that's, to me, at least in this particular part of the physics, some kind of dark photon is, in theory, the most promising candidate for the remaining questions we have for the hadronic vacuum polarization, particularly.
And how do you experiment for that?
It is challenging. I think there are a number of experiments that should, in principle, be able to detect it to some degree of precision. There are sort of these dark matter direct detection experiments that look for any kind of what they call a dark matter wind, and a dark photon could play a role in that. And so therefore they should, given particular types of dark photon, they should get a signal at a particular level, whether it's above or below their sensitivity, depends on the exact parameters of the dark photon. And then also we should, in theory, be able to see it eventually at various collider experiments.
Is there any possibility that it really is just a play with gravity, that gravity does change over distance? Something that would annihilate the need for dark matter at all, I'm saying.
Yeah. I think it's a tempting explanation. I think it would be very exciting if that was the case. To the best of my understanding, none of the proposals for how to do that are especially promising at this stage, but I think it's definitely an avenue that we should explore. We shouldn't just assume that it's the thing that seems most plausible to at least the particle physics community, that particle physics isn't the only possible explanation. We should definitely keep exploring whether there is some kind of modification to gravity. So far, the most promising avenues have all been in particle physics. So far, most of them have then later closed off or become significantly restricted in some way. So it looked the most promising, but we haven't found anything there. So as you say, maybe we will end up finding that it actually does lie elsewhere.
Yeah, Muon seems to work well on certain scales, but not others.
Yeah. To me, the most interesting thing is related to why I think there might be this dark photon and what it is different about this new calculation, which is that my group did, taking the mathematics of the standard model, we did a calculation where we directly put that onto a supercomputer and computed the results that it predicted. All of the previous results that were in tension with the experimental result were all calculated in a different way. They took data from experiments from electron-positron colliders, where they collide an electron, an anti-electron, a positron to produce particles, and particularly to produce a photon, and then that will decay into various things. And they used the data from these experiments, and they used particle physics to then relate that data to the specific physics of the muon magnetic moment that we wanted. So there was a big difference between that result, which very much took a large body of experimental data as input and then related it to the result we wanted, and our result, which took just the standard model and the small set of parameters, just the quark masses and the coupling of QCD force and then the strength of electromagnetism, so the coupling of strong force and electromagnetism, and did this numerical calculation. And so what this seems to indicate is that given there's a significant discrepancy between the two, and one of them agrees with the final experiment and one of them doesn't, that there is some kind of tension between the standard model and these other experiments, these electron-positron colliders. And this is where I think this potential, it has been proposed that a dark photon could explain these discrepancies. And there are further, in more recent experiments, there's even discrepancies among different electron-positron colliders operating in different ways. In some sense, it looks like a dark photon could theoretically bring them into alignment with each other. Other experimental limits that other experiments in theory should have seen a dark photon with the properties you need to do that. So there would have to be some additional physics to explain why we haven't seen that dark photon anywhere else.
That's Dr. Finn Stokes from Adelaide University. And this is SpaceTime. Still to come, the evening skies of Sydney light up as a spectacular meteor plunges through the atmosphere. And later in the science report, a new study has found the positive effects of vitamin C in combating some types of cancer. All that and more still to come on SpaceTime. The evening skies of Sydney and much of the New South Wales Pacific coast were lit up on Thursday evening by a spectacular meteoroid burning up in the atmosphere. And the bright green fireball was visible far beyond Sydney's metro area, with reports as far afield as Junee and Canberra in the south, Bathurst and Mudgee in the west, and even as far north as Queensland's Sunshine Coast. Witnesses described the celestial display as producing a rainbow of colours from blue to green and even orange, briefly turning the ocean an electric blue before eventually disappearing over the Pacific horizon to the east. Now, in astronomical terms, this meteoroid is classified as a bolide. Bolides are fireballs that are brighter than the planet Venus and are seen to airburst or break up as they enter the atmosphere. Astronomer Brad Tucker from the Australian National University says despite its brilliant display, the meteor itself would only have been around 30 to 50 centimetres wide. He says its predominantly greenish colour was caused by its iron and nickel composition. It was moving at over 30 kilometres per second, much too fast to be space junk, which typically streaks through the atmosphere at around 8 kilometres per second. And its flight path also rules out it being part of the annual Eta Aquarids meteor shower, which is visible between mid-April and late May. Certainly a spectacular celestial display as Australia moves closer to winter. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with a science report. The World Health Organization has declared an Ebola outbreak in Central Africa around the Democratic Republic of the Congo and Uganda as a major public health emergency. Ebola is one of the world's deadliest infectious diseases, with several different viral strains causing severe outbreaks, especially the Zaire strain. Now, this latest outbreak involves the Bundibugyo strain, which kills about half of all those infected, and for which there is no vaccine. Ebola spreads directly from person to person through contact with infected body fluids. The first symptoms include fever, a sore throat, muscle pain, and headaches. These are usually followed by vomiting, diarrhea, a rash, liver and renal dysfunction, and extensive bleeding both internally and externally from the eyes and from mucous membranes, including from the gastrointestinal tract. Death, if it occurs, follows typically between 6 and 16 days from the first symptoms, and is often due to shock from the loss of fluids. A new study claims vitamin C affects chemical reactions in the digestive system that are linked to cancer. The findings, reported in the Journal of Theoretical Biology, looked at North American diets, which have seen a steady increase in exposure to nitrite and nitrate compounds, which are commonly found in cured meats, as well as fruits and vegetables grown using polluted soil and water. While nitrates and nitrites play an important role in neurological and heart health, in the stomach they can undergo a chemical reaction known as nitrosation, resulting in the formation of chemicals that many scientists suspect increase the risk of cancer. The authors developed a mathematical model of the salivary glands, stomach, small intestine, and plasma to simulate how nitrates and nitrites move through the body and change over time. Their model demonstrated that when vitamin C is also present in food, such as in leafy green vegetables like spinach, which contain both vitamin C and nitrate, it could decrease the risk of cancer. The study also suggested that taking vitamin C supplements after each meal could have a moderately positive effect in reducing the formation of nitrosation products associated with cancer risk from dietary nitrates and nitrites, such as those found in foods like bacon and salami. A new study has supported the long-standing theory that the forearms of some theropod dinosaurs grew smaller and weaker as their heads grew bigger and more powerful. The findings, reported in the journal The Proceedings of the Royal Society B, looked at data for 82 species of theropod dinosaurs. Theropods are the large two-legged, mainly carnivorous dinosaurs such as Tyrannosaurus rex. The authors found that smaller arms were closely linked to the development of large, powerful skulls and jaws, more so than to larger overall body size, indicating that having tiny arms weren't just a byproduct of bodies getting bigger. The paleontologists behind the study say that as their prey grew bigger, the heads of these theropods took over more and more function from the arms as the primary method of attack. The authors say strong skulls and jaws evolved to better subdue the prey, and it became a case of use it or lose it, with the arms being less and less useful and consequently reducing in size over time. The other primary theory for the reduction in arm size in animals like Tyrannosaurus rex is that as their heads grew bigger and heavier, the arms had to reduce in size in order to maintain the correct balance between the front of the animal and the tail, thereby preventing these archosaurs from literally tipping over. Fake moon landing conspiracy theorists have been forced to admit defeat following multiple images from independent sources clearly showing the Apollo 11 LEM, or lunar lander, just where NASA said it was in the Sea of Tranquility. But it looks like these conspiracy theorists will go down kicking, as they've already come up with a new conspiracy theory claiming that yes, Apollo 11 did land on the moon, but they found aliens there. The skeptic's Tim Mendham says, according to this new theory, NASA have been hiding the truth all along.
This is someone who believes that they really saw something up there, and it was aliens and extraterrestrials having a little camp up there or something that they saw. Must have been a flyover, and they saw this, and because naturally it was hidden, but it's saying that therefore, the moon landing vehicles did go to the moon.
They can't sort of deny Apollo 11 anymore because they've actually seen the lower stage of the lunar lander, the LEM, sitting there. They've taken photos of it, so we know it was there. Plus, of course, there's the radar reflectors and all the other stuff. I'm old enough to remember Apollo 11, and I remember all the footage I saw of the landing, of the EVAs, the lot. During none of that did I remember seeing any little green or little grey men wander up and knock on the door asking for a cup of sugar.
And would you like a slice of cheese?
You know, cheese is just a loaf of milk, don't you?
A loaf of milk, yes, thank you. Anyway, this is supposedly that the Apollo 11 mission flew over the top. One of the nicest quotes in this story is that the story claims the astronauts communicated privately on a secret radio channel during a communication blackout.
If there's a communications blackout for some reason,
side of the moon.
Why would you need... Well, no, because that side of the moon's always facing the Earth anyway. Why would you need a secret channel?
Yeah, I know. There's a lot of things in these stories that sort of don't really hold a lot of water. Anyway, there's supposedly psychics who predicted that there'd be aliens on the moon, and of course H.G. Wells wrote a story about first men in the moon, and all these sort of things. That the delays, quite reasonable delays to the Artemis 2 launch, to say that they're delaying it because they don't want to reveal what's really there. No, it's another one of those stories that the conspiracy that will disappear.
That's the skeptic's Tim Mendham, and this is Space Time. That's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from SpaceTimeWithStuartGarry.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to SpaceTimeWithStuartGarry.com for full details.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.